Okay, I'm gonna start recording. Okay, we're recording. So let me turn on the camera so I can memorialize this. So for folks on Zoom, God, how do I turn off the blur? Oh, great. We got a letter from with a little bit of code at the front. I will say, guys, like that you're not making use of this function because you're printing out thank you. But I like it. I like it. So if you're on Zoom and you want to come join the celebrations, please do so. I thank you so much, guys. This really means a lot to me. I will read through all of these and I will let me share the photo we just took on Piazza so folks can have a copy of it. And wow, I'm gonna miss you guys. You better come to the Bay Area at some point, all of you. Yeah. I'm sad. I'm sad. We're moving on to. You guys will be moving on to bigger and better things. So what class comes after this for most of you? Who's graduating? We've got a few seniors here, right? You guys should be super excited. Yeah? Not Jonathan, yeah. He came to say oh man, this is taking a little longer than I thought. I have to upload one by one. Okay, I'll post just this one. All right. Oh well, that's just oh, that's cheese. That's cheese picture. Okay, I'll add the other ones because we gotta get started, guys. It's not over. It's not over. You still have. Oh, I like that poster. I beat Comp 285. It's really good. It reminds me of my yeah, there we go. Okay, maybe I should get more folks in here too. Can I? Oh, am I getting everybody? Okay, I got everyone. There we go. 3, 2, 1. Yay. I got it. All right. Okay, bringing it back. So we still have some pizza left if you want to grab some. Reminders. All right, you guys are not done yet. I know this is very celebratory. News to you guys, I will not be coming back next semester. So I just did it for this. You guys are the only class in all of MCAT that will have me as a professor for at least for the foreseeable future, I would say. So, but I am going back to the Bay Area, back to software engineering, probably at Meta, maybe somewhere else. I don't know. I'll keep you guys updated. If you're ever in the area, reach out to me. And for you guys personally, you still have your final exam. So hopefully you're studying for that. I'm going to make it really, really hard, as hard as I can, just to make sure that I get a lot of you fail. No, I'm kidding. I don't want to fail anyone, but it is going to cover a lot of stuff. So please study for that. Also, congratulations. I believe we're at maybe 56 plus, which puts you at above 90%. So that means the whole class gets 1 percentage bonus point on their final grade. For this part, that's really all to you guys. And then for the course evaluation on Blackboard, we're still at 20%. So log on to Blackboard, fill that in. If you can fill it in, that's another 1%, okay, for the entire class. If we get to, what's it, 70? Did we say for this one, 70%? We said 55. You know what? I think I remember 55. I think that sounds right. Yeah, I'll double check. But yeah, just try to fill it out. And then we took a picture. So thank you guys. I will remember all of you. And if you ever need referrals to wherever I'm working, just email me, send me your resume. I'll submit them right in. You guys know that I get money every time you actually get the job. So don't ever be shy to like ask people for referrals. They usually want to refer you, especially if you're going to get the job, you know, like, yeah. But all right, let's wrap up. So this is our last review lecture, and we're going to pick up where we left off yesterday, on Monday, which was with dynamic programming. So here was the problem we were talking about. Again, you have a vending machine that dispenses n different types of snacks. Snack I has a certain number of calories and a certain cost. We assume that the vending machine will never run out of any snack. And the problem is that you're given X dollars and you want to buy the snacks that give you the most calories, given that you only have X dollars. So here was we tried a couple of greedy algorithms for this, and none of the greedy ones worked. Who remembers what were the two greedy algorithms that we talked about for this problem? Yeah. Yeah, so one greedy, and again, this does not work, right? So this algorithm does not work for this problem. But one possible greedy algorithm that you could think of is, let me buy the snack that gives me the most calories per dollar, right? So we found that, we tried it out. It did not work. It turned out that it's not optimal to do that. Another even more straightforward greedy algorithm is, let me buy the snack that gives me the most calories. So ignore the price, let me just get the most calories. None of those greedy algorithms work. So what we're going to do instead is we decided, hey, let's use dynamic programming. So dynamic programming basically almost always works. And the question that we're looking for here is, we decided to we initialized an array of zeros called DP. So DP is going to be an array that is going to start with a bunch of zeros. And its size is going to be X plus 1. Okay. And then what we said is, we're saying, what is the sentence that describes what is DPJ? So if I do, DP of 4, I want to know, what is this? Like, what does it represent? And I think you mentioned, so one way to look at this is you can consider that 4 here is the index for the array, and the array is of size X plus 1. X represents dollars. So you might assume, or you might consider, hey, this 4 probably has something to do with dollars, right? So if you follow that logic, it actually turns out that here the J is talking about snacks. So it's not this one. Here the J is talking about, here the J is talking about buying only snack J. So it's probably not this one. And here the J is talking about snacks again from 0 to J. So it's probably not this one. And then the only question that remains is, out of these two, does any one of this seem reasonable to you, right? And it turns out that this is a very reasonable way to define subproblems, right? So instead of solving just our initial problem, which is, what is the maximum number of calories I can get with X dollars, where X is like, 10, it's fixed. Now we're going to try to solve all of these smaller problems. So we're going to try to solve, we're going to solve DP0, which is, max calories with a $0 budget. So if I have no dollar budget, we're going to try to solve DP1, DP2, and so on until we solve DP of X, right? So that actually leads us to the next question, which is what should our base cases be? So these are all of our subproblems. What are the easiest problems that you already know the answer to? Yeah, go ahead. Yeah, so one of the simplest base cases is just dp of 0, because this is saying how many calories, what is the maximum number of calories I can get if I have a budget of $0? And the answer is 0. And that you know that is correct. That is the obvious answer. Are there any other base cases? Yeah. 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 So here's the other thing, like we talked about this in computer science a lot. There's many different ways to solve the same problem. So it wouldn't be wrong to have a base case of dp1, right? Something like this, because you're saying, hey, this is actually kind of easy to solve. Maybe I iterate over all of the possible, snacks I can buy. And if there's anything that's under $1, you know, maybe I just buy one of them. So it's basically, hey, if I'm only buying one of them. Now, what I would say is like, you could define this as a base case, but because you're already trying to like it's not obvious, it's not immediately clear to me what the answer is. Like, it's not a constant. It might be like, hey, let me look at all the snacks. Let me like do a little bit of work. I would say it's actually okay to not have it as a base case, right? So in general, I would say our only base case is this one. And you can have other base cases, but they're getting a little bit more complicated. Okay, cool. All right, so now that we have our base case, we can think about this. So I give you this partially, and I want you to fill in the blank, essentially. So we are trying to figure out dpj, which is max calories I can buy with $J. Okay. How would you figure this out, assuming that you have answers to everything J minus 1, J minus 2, everything smaller than J? Yeah. Oh, were you raising your hand? No? Yeah, yeah.
I can't intuition, but I think I remember it was like you take the max of the J minus 1, including the one that you're at right now, or the one that you're at, or just the one that you're at, right? Something.
Okay, close. Not quite, not J minus 1, but you are right. There is the idea of if I'm trying to figure out how many calories I can have with a budget of J, well, one obvious thing I can try is just for every single snack, what if I bought that snack, right? So what you might do is, again, we're iterating from 0 to n minus 1. So you might say, well, the maximum number of calories is going to be calories of the ith snack, because maybe I buy the ith snack, right? Plus, what is plus what? What would I add here? So I'm saying I'll definitely buy the ith snack. It is not I minus. It is not I minus 1. It is not J minus 1. But it does have to do with minus something. You are definitely doing, and you want to use the fact that for all values smaller than J, you have the answer. You know dp. So, if J is 10, then dp 0 all the way to dp 9, these are already filled in. You already know the answer for what is the maximum amount of calories you can get with a budget of $9, of $8. Okay. Yeah, Vincent. Yes. So there is something to be said. Yeah. So you do J minus the price of the ith snack. and you would use that to look up the answer, right? DP. Okay. So this is, again, and we're not done. We're not done yet. This is part of it, right? So if I bought the ice snack, I would get this many calories and I would have this much money left over, J minus the cost of the ice snack. So I could say, let me buy this one. And then what is the maximum, what is the most amount of calories I can get for this cheaper, for less money that I have? Okay. Now, there's a lot of i's, right? I'm going from 0 to n minus 1. What do I do with all of them? So what is so dpj is actually equal to what? So here I'm just, right now I haven't said how to aggregate my answers. I just said for every I, let me compute. If I bought this snack, this is how many calories I could get. Yeah. Sorry, what was that? What if you don't buy the current snack? Not quite, because we are considering, again, we have an infinite number of like for the ice snack, we can buy as many as we want. So the fact that we bought it is not actually impacting whether we can or cannot buy it in the future. But yeah.
So you would take the maximum of them?
Yes, that's it. So you want a way to aggregate it, right? Because what this is doing is we're saying, hey, I'm for sure going to take the ice snack. How many calories could I get if I for sure take that one? But the answer to this problem, DPJ, is not, take the fifth snack. It's out of all the possible ones you could take the one that gives you the most calories, right? So you would replace, you might write something like max, of this, right? So you iterate over your for loop, you calculate these numbers, you keep track of the maximum that you've ever seen. What's another thing that we're missing here? What's an edge case that we will run into? Can I always take the ice snack? When can I not? Oh, actually, maybe this is what you were, is this what you were referring to, right? Okay, I'm sorry, I totally misunderstood what you said. All right, yeah, so when can I not take the ice snack? Yes, so in addition to just calculating these values, we actually want to make sure that we only take the values where we can buy the ice snack. So we would have an additional if statement here to check that the price of the ice snack is less than or equal to J. Because only if we can afford it do we actually take it into consideration, right? Now that also serves the purpose of what is the smallest, so J minus price I, what is the smallest this index can be? Because I am checking this value. Zero, right? And that makes sense because the problem is if I don't check this, another way to think about it, if I don't check this, I might get 10 minus 11 and I'll have a -1 and you're like, let me look up the answer for -1. You don't have the answer for -1. You're going to get invalid index error, right? Cool. And that's actually what the next question actually asks, which is what are some special conditions that you need to watch out for, which is you can only consider it in your maximum if you have enough money to buy it, right? Next question, what order should we solve the subproblems in? What order should we solve them in? Where does our for loop start? Do we start with I equal to n minus 1 and we fill in the array backwards? Or do we start with I equals 0 and we fill it in forwards? Yeah, go ahead. From the beginning to the end. So we fill them in starting, well, obviously I equals 0, we already know the answer. It's our base case, right? Or sorry, J equals 0. And then we would fill in J equals 1, why? Why is it okay to do J equals 1 next? Yeah. Yeah. Right. So if we, well, I didn't save it, but if you guys notice when I wrote, the answers, they all depended on values that were smaller than J. So by filling it in from 0 to 1 to 2 to 3, that guarantees that every time I'm filling in the j's value, I already have the answers for everything before it, right? And that is a dynamic programming problem. What is the time complexity of this dynamic programming problem? So if you guys remember dynamic programming, all of the algorithms do a couple of things. They create some space, storage, to save our answers, right? And then we fill in that space, right? So for the time complexity, generally, one way to try to think about it is how many steps does it take you to fill in one thing in your storage? How many things do you have to fill in? Yeah. O of, it's not O of n, but you are right that it is linear. It is. So n is the number of items I have. How big is my storage? J is the index. What is, yeah, J is like the dollar number. Do you guys remember? It's O of X, capital X. Because if you guys remember, we said the array DP is going to be of length X plus 1. Because X is the amount of money, right? So it actually doesn't matter. Like the algorithm is going to take more time to run, even if you have just 2 items. The way the algorithm works is it goes one by one based on how much is your budget, right? So the bigger your budget, the longer it's going to take to run. And that's why we say that the running time is O of X. And that is correct. It is O of X. And one way to think about it is you have to fill in the array, which has size X plus 1. So that's going to be O of X. And then to fill in each item, it takes constant time. I was wrong. This is wrong. It's not complete. Yeah, somebody takes linear, takes O of, can you be more specific than linear? So if we go back to this, how long does it take me to fill in each J? N, takes you N. So there's X J's, and for each one, it takes me N time. So actually, the complexity is O of N X. I'm sorry about that. Does that seem a little clearer to folks? Yes, O of NX. If you guys remember, this is a very similar problem to the knapsack problem that we covered in lecture. Okay, so let's go ahead and move on to the next one. So here's another dynamic programming problem. So we have a robot that is located at the top left corner of an M by N grid. The robot can only move either down or right. So he can only, so from here, he can only go to this square or this square. Those are the only options. If he's here, he actually gets stuck. He cannot go down, he cannot go right because these represent walls, okay? Now the robot is trying to reach this corner, the bottom right corner of the grid, but there are some squares which are magnet traps, so the circles that the robot cannot step on. So it's okay if he is next to these circles, but he cannot go on them, okay? Now the question is, how many possible ways, how many possible paths are there for the robot to go from where he started to the bottom corner of the finish? So for example, in this case, there's actually just one, there's one path here, and there's another path here, and there's another one here. So there's actually 3 paths, okay? But the question is obviously in general, not just for this example, okay? So think about that in the back of your head. Here's what the question on the final might actually look like. So this is what we're gonna do. We're gonna initialize a 2D table of size M by N. So this is gonna be a matrix. How should we define dp of ij. So in English, what does this represent? David? In a way, yes. So ij probably, because like if we think about it, right, we say this table is of size m by n, and the grid the robot is walking on is m by n. So I and j are probably locations of something. The robot is probably a good guess. So that's the location of the robot, right? But what would be, so this is going to be a number. It's going to be a single number. What would that number be? What would it mean? Where ij is the location, yeah. So this is different. So assume you are already given as input grid ij. This is going to be, let's say true if we can step on it, and then false if we can't. So that's separate. So now every time you see me say DP, it has to do with dynamic programming. So I'm trying to define smaller problems to try to help me solve the bigger problem. So the original problem, if you guys remember, is how many possible unique paths are there? Okay. So what might dpij be? Yeah. Okay, very close. Yeah, I think you might actually be right. So again, for dynamic programming, right, our final goal is to find out the number of possible paths. Okay. Now, what I'm trying to introduce to you is I'm going to say, hey, it's actually pretty hard to do that. I'm actually not even sure how to find all the possible paths. Like maybe I run DFS, maybe BFS. There's a lot of ideas you can think of, right? But if I'm going to try to do it with dynamic programming, the first step I'm going to do is I'm going to define my sub problems. So smaller problems that help me solve the original problem. So what this actually means is dpij. So this is going to be a number that's going to say this is number of paths from number of paths the robot can take if he starts at ij. Okay. So now I have created a ton of subproblems. I have a lot. So now, I have dp00, which is, what is dp? So let's say we start 0, 1, 2, and then 0, 1, 2, 3, 4, right? This way. So let's say this is 0, 1, 2, and this is 0, 1, 2, 3, 4, 5, 6. Let's just say we number them that way. What is the one answer that we want? What is the answer we're looking for? Yeah. You're probably thinking about the base case, right? So yeah, so there's two things. So once we have this definition, okay, the next thing you ask is, what are the base cases? So yes, what would be, so in this context where 0, 0 is going to be the top left corner, so it's going to be this corner where the robot always starts, and then we always are trying to get them to the bottom right corner. What is my base case? What is the thing that, like, the number of paths from the robot that the robot can take if he starts at ij? For what values of I and j do you know the answer? So 0, 0 is going to be this corner. So actually, I don't know the answer to that one. Yeah, go ahead. Yeah. 2, 6. Yes, for this case, 2, 6. In general, what are the variables that I would use? Because remember, this grid, this is an M by N grid. So M as in, like, it has M columns. So in our case, it has 3 rows and 7 columns. So this is a 3 by. So this case, you are right. It is 2, 6. That answer I know. In general, how do I represent what are, yeah, Serena?
N-1 or the size of
Yeah, one of these two. I think n-1, n-1. I might have those backwards, so you guys think about it. One of those two. So for this problem, that is my base case, because what is the answer? If my robot starts at the finish point, how many paths are there for him to get to the finish point? Not quite. One. The answer is one. There's one path, which is like he does nothing. He's just there. That's because like 0 paths is kind of weird. I mean, you might try 0. I wouldn't take off that many points if you said 0, but like it is 1 in this case, and it's going to become clear later. So this is the base case. Okay. In this syntax, what is the answer to my original problem? What is the answer I actually want? Yeah, Leander. Yes. So I am looking for DP 0, 0. Because what is that going to tell me? That is going to tell me the number of paths the robot can take if he starts at 0, 0, which is the original problem. That is the original problem. So that's what I'm looking for. I know the answer to this corner, right? So let's change slides for a little bit. So again, the base cases we talked about. So now let's talk about how do we actually solve this? What is the recursive formulation for this? So on this side, we have dpij. So I say number of paths if robot starts at ij. So let's say the robot is starting here. So again, in our case, this is 0, 0, 4 something, but let's say it's some arbitrary ij. Now, how might you count the number of possible paths? Let's say ij is this. Let's say we're here. So let's forget this one. Let's say we're here. We already know the answer for this is 1. Or actually, very, very close. So sorry, I've been drawing a lot. So we know the answer for this one is 1. So we have 1 filled in. Now, how would you find the answer to this square? So what is the total number of paths that the robot can have if he starts here and he wants to get to the finish line? Yeah, go ahead. It's just 1. The answer is it is just 1 path. Did you find the path, or is there? So let's keep going. Let's fill it in together. So let's say I'm here. What are the number of paths? 1. Okay. Let's say I'm here. What are the number of paths? 1. Okay. Let's say I'm here. How many paths? 1. Let's say I'm here. How many paths? 2. Okay. Let's say I'm here. How many paths? 3. Okay. How did you guys figure that out? Yeah. What do you guys think? So what this is saying if I want to figure out the number of paths from this square, there's one option. He can go right. And that's going to be the number of paths from I plus 1 plus j. So it's going to be this 1. Plus, the other option is the robot to go down. And that's just going to be how many paths are there in dpi j plus 1. So this is 2. And that's how I get 3 here. I mean, we can continue, like how many paths are here? He can either go right, so there's going to be 3 paths, or he can't go down. So actually, what are some edge cases I want to consider here? Yeah. Yes. So you want to add a statement where you only include this value in the sum if there's no magnet there. Right? So in this case, we would only do 3 plus nothing because there's some magnet going down. How many ways are there for this square? He can either go this way, so that's 3, or he can go this way. We haven't filled this in. How many paths are in this one? 0. Why? Because what's another base case that we have then? What's another base? So in order to calculate this, this is 0. The answer is 0. But how do we know it's 0? Yes. So if you have any spots where you cannot go down or right, the answer is 0. So that is yet another base case. Another way to do that same base case is you can actually say the answer is 0 for all the magnets. That's another way to do it. And then you can imagine you can keep filling this in. So again, for this one, I can only go this way. So the answer is going to be 0. That means this is going to be 0, which means this is going to be 3. This is going to, I have these 2. So this is 0. This one's 0. I have these 2. So this is 0. And then this is 3. And then this is 3. So now I actually have the answer that the number of paths is exactly 3. And that's it. You guys solved that. That is how you solve this problem. Does that make sense to most of you or some of you? Okay. And there are, okay, maybe not. Maybe try to revisit this one because this is the meat of dynamic programming. But there are some special conditions that we talked about, right? So you want to make sure your base cases get filled in. You want to make sure you only look left and right. There's also some conditions when you get to the edge, because here we only looked down because we can't go to the right, right? Cool. What is the time complexity of this dynamic programming approach? How many things do I have to fill in, and how much time does it take me to fill in each one? Yeah, Yes. So there are m by n spaces I have to fill in. And if you guys remember, each one, I'm just adding 2 numbers. Maybe I'm checking some extra stuff, like, are you at the edge? Is there a magnet, right? But I'm just adding 2 numbers and checking some stuff. So that's constant time, which means the running time is m by n. Cool. I'm going to skip this brute force one. I encourage you guys to take a look at it. It's pretty interesting, but in the interest of time, we won't have enough time to do it. Okay. Yeah, we might not finish reviewing the practice exam because we only have 3 more minutes left. All the solutions are posted online, so you can look at those. Last 3 minutes. So we have the Kiwi bird, we have MSTs, actually, and then we have network flow, and then we have P versus NP. Wow, we did not get through a lot of stuff. Any of these you guys want to cover? Any section that is like, yeah, let's do that one. Okay, residual graph, any other votes? I'm also happy to stay for an extra 10 minutes, but you guys probably have class after. So. All right, so let's do network flow. Okay, so this question asks you, given this graph, where this is the amount of flow and this is the capacity. So what does this say? That says that on this edge, I am pushing 2 flow, but my total capacity is 3. I want you to draw the residual graph. What's the first thing you do? Or yeah. Yes, the residual graph is the graph that has the reverse edges going back to see how much you can actually push back. So the very first thing I would do is I would just copy all the nodes. Okay. And then what do? You look at each edge. So this edge has flow 2, capacity 3. So that means there's an edge going forward with 2, because that's how much I'm pushing. And then I'll put an edge going backwards with 1, because that's how much. Oh, I actually messed up. Who can correct this? Yes, David. Okay. You have not a cut. I'm trying to get the edge from V1 to V3. Who knows what those edges look like in the residual graph? The edge going forward is actually how much capacity is remaining. The edge going backwards is how much capacity I'm pushing. So yes, so the edge going forward here would be 1. The edge going backward would be the 2. So I got the order switch. And then you do that for the rest of them. So the edge going forward here would be 2. The edge going backwards would be 3. Edge going forward here would be what? For from S to V2. It would be 0, so you don't put an edge. And then you have an edge going backwards with capacity 2, right? And then you do that for the rest of the edges. So that is how you construct the residual graph from the original graph. Okay, so you should be comfortable doing that for the final. Okay, so let's actually finish this up. Do we have time to fit? Okay, well, it's 12:50. Are you guys, do you guys want to stay and finish this problem up, or should we? Okay, so I'm going to try to finish this up. So 3, 4. So for this edge, what do my edges look like? The edge going forward is 1. The edge going backward is 3. What about for this one? 1 going forward, 4 going back. What about this one? 1 going forward, 1 going back. And then we also have these edges in the middle. So for this edge here, we have 1 going forward, 1 going back. And then for this edge, we have 0 going forward and 1 going in reverse back, right? So that is what our augmented graph looks like. The next question is identify an augmenting path. So is there a path on this graph from S to T? Yes. So the idea is just pick one of them, pick any of them. So let's say we pick this one, maybe. That's a path. That's a valid path from S to T. How much flow can I push on that path? 1, because the smallest edge along the path has capacity 1. So now I say update the flows to reflect the increase flow along the path. So that means that instead of 3, 5 here, if this is going forward, I can actually push an extra 1. So this is going to be 4, 5. This 2, 3 is going to become 3, 3. It's going to get saturated. And this 1, 2 is going to become 2, 2. What's an edge case here that we didn't cover in this example? If I'm pushing flow through a backwards edge, then I have to decrease the flow in the original graph. If you guys remember that, right? So you do need to remember which edges are like going forward, which means they're going in the same direction as the original edge, and which are going backward, which means they're going in the opposite direction. If your path in the residual graph pushes flow through a backwards edge, that's actually telling you decrease the flow along that edge. Okay. Here's another one. So this is more about reductions. It's a little bit, yeah, I'm happy to stick around. I guess they'll kick us out at some point. You guys can also, I'm still recording, so this will be fine, but let's walk through this problem. Yeah, I guess that's it. I guess you guys will just look at it online. Or actually, if you have questions, you can come with me to Eric. I'll still be there for a few hours and I can go over the rest of this. Yeah, Serena? I mean, you need to know that like a hash map takes O of 1 time, and you should know that like a hash set takes O of 1 time. is like highly unlikely I would ask you to like make a hash function. Yeah, probably not. Yeah. Cool. All right. Thank you guys. And thank you so much for the card. I appreciate it. Thanks. So thank you for the picture as well. I'm going to share it with everybody in my team. They're going to be so happy. Yeah. And yeah, I'm going to be in Eric. I'm still around before the final. If you want to meet in person or something, just like email me beforehand because I might not be on campus, but I can come. And then, yeah. Oh, I am not here next week. I'm in California, but I can meet on Zoom. Also, I'm here, like I'll be in person in Greensboro until Saturday today. And then I will come back to Greensboro on the 19th of May. I have to go do like a citizenship interview for USCIS, but yeah. Yeah, this Friday works. Yeah. Yeah, Eric is fine. Yeah. Sure. Yeah. Yes, I can do that. Yeah. Oh, wait, emails for.
Not the school emails, because like once you go
Right. Oh, I will make a. All right, if anybody cares, this is that's my email, and that's my LinkedIn, my personal stuff. I will leave it on the slides. Oh, wait, okay. Sorry. Let me move it. I guess I could, should I give you my, yeah, phone numbers? That's fine. Yeah, so if you, yeah, my LDAP on LinkedIn is Nautilic, and then that's my personal email. So I've had that since middle of high school, I think. So I'll have it for a long time. So if you ever need to get in touch with me, this is probably the best possible way. You can also message me on LinkedIn. I check that every now and again. But yeah, and I'll leave this on the slides. They're posted on the course website, and then I'll post on Piazza as well, just to give you guys. Yeah. Yeah, probably. Yeah. Comp 285. I will keep it up probably for at least a year, because I think I have the domain for like another year. I might not renew it. It'll probably still be up because it's on GitHub. So that doesn't cost me anything, but it just won't be at comp285.ml. It'll be like, I think it's like algorithmscourse.github.io or something. There's like another URL that gets you the same place. Yeah. Cool. All right, let me end on Zoom. All right, thanks everybody on Zoom for coming.